Hi, I'm Kartikey Gupta, and my focus is solving the compounding multivariable barriers preventing telehealth access in rural and indigenous Alaskan communities. These communities operate under extreme geographic constraints, hundreds of miles of physical distance from medical centers, seasonal isolation when ice roads melt or weather grounds flights, and broadband costs that routinely run 2 to 8 times the national average. Measuring these barriers reveals a critical data problem. Major federal agencies track infrastructure in isolated silos. The FCC monitors broadband, CMS logs healthcare facilities, and the Census Bureau tracks income. Because these datasets are never programmatically cross-referenced, policymakers are left with a massive analytical blind spot. A community might appear served on an FCC broadband map, and CMS might show a registered clinic nearby. However, if that local clinic is separated by an unnavigable river, and basic broadband costs 4% of the local median household income, telehealth remains entirely inaccessible. True telehealth readiness cannot be determined by single data points. It requires synthesizing affordability, physical proximity, and digital connectivity into a unified programmatic system. This is the interactive map dashboard for the current working prototype of TENeT, the Telehealth Effectiveness and Necessity Tracker. The architecture spans 12,450 lines of code driven by a fast API backend with 17 REST endpoints feeding data to this React and Leaflet interface. The prototype's engine uses the UN Broadband Commission standard, capping affordable internet at 2% of monthly income as a strict mathematical gating mechanism. By calculating this ratio against facility proximity, the engine routes communities into 3 tiers: ready, supported, or excluded. While the analytical approach works from end to end, the current system relies entirely on synthetic placeholder data. The income proxies, broadband speeds, and facility records are fabricated inputs, meaning every result, while logically sound, is currently disconnected from reality. There is also a secondary architectural limitation. The current SQLite database relies on simple bounding box math for its spatial queries. At Alaska's extreme northern latitudes, calculating distances by approximating the globe as a flat grid introduces significant geodetic errors. My Google Summer of Code proposal targets these exact limitations. To evolve TENeT into a research-grade tool, the synthetic data must be replaced with live production-grade federal data pipelines backed by a geographically precise database. This system overview diagram maps the first technical milestone, constructing 3 distinct extract, transform, and load pipelines to replace the placeholder data with verifiable metrics. Here, in the Census and Gesture code snippet, you can see the first pipeline. It queries the Census Bureau API to pull American Community Survey 5-year estimates, locking in accurate median household income data for every community. The second pipeline tackles the FCC broadband data collection. The engineering challenge here is scale. The FCC reports data across 4.7 million national census blocks, which must be accurately filtered and mapped to Alaska's 20,000 blocks. The algorithmic solution joins the FCC records on specific FIPS codes to compute the population-weighted median speeds for each community. Taking the median speed is crucial. Maximum speeds artificially inflate a community's true available bandwidth. This CMS ingester snippet outlines the third pipeline, which extracts CMS bulk data and uses taxonomy mapping to geocode and verify over 500 individual healthcare facilities across the state. Once these 3 pipelines are operational, the application will compute equity classifications using programmatic ground truth for over 200 Alaskan communities simultaneously. Alaska spans from 51 to 71 degrees north latitude, introducing a unique spatial database challenge. SQLite's bounding box approximations distort distances near the poles because longitude lines physically converge the further north you travel. A standard search square becomes highly inaccurate when trying to locate a nearby clinic in the Arctic. The migration strategy resolves this by upgrading the backend from SQLite to Postgres. At the database level, this allows the implementation of proper SRID 4326 geometry columns, treating the Earth as a sphere rather than a flat grid. This upgrades both accuracy and performance. The system replaces slow Python-based have assigned calculations with PostGIS GIST spatial indexes, executing sub-second geodetic proximity queries directly in the database. With geodetic rigor, when TENeT calculates a rural clinic is 50 kilometers from a remote village, it is a mathematically exact research-grade certainty. While binary gating identifies if internet is affordable, it cannot rank communities. To measure exact degrees of exclusion, the backend must evolve into a continuous 0 to 100 composite scoring engine. This data flow diagram outlines the Telehealth Readiness Index. It evaluates 5 dimensions of community readiness, computing independent scores. The connectivity score measures download, upload, and latency against a strict baseline floor, the minimum required for stable telehealth video. The affordability score replaces the rigid UN threshold with a graduated scale based on the precise ratio of local broadband pricing against income. The healthcare access score utilizes new post-GIS distance queries, weighting the density and CMS capability of nearby facilities. The final two variables, transportation and seasonal resilience, account for the severe limitations of physical infrastructure in the Arctic. By calculating a continuous, multidimensional ranking of exclusion severity, the TRI provides researchers and policymakers with an exact numerical target for intervention. The integration of federal data and geodetic accuracy transforms the platform into a dynamic policy simulation engine. This simulation interface shows how the fast API backend is extended with a predictive endpoint. Using these slider controls, researchers can inject hypothetical variables into the algorithm. As the math executes, the math markers respond dynamically, shifting colors from excluded to supported in real time. This creates a predictive sandbox, giving a mathematically backed answer to the question which exact communities will benefit most if we deploy this specific subsidy. Delivering this architecture requires a 350-hour engineering commitment to build the production ETL pipelines, migrate to a PostGIS architecture, and deploy the TRI scoring engine. To ensure data integrity and reproducibility across the platform, the final pull requests will include over 80 automated validation tests. The outcome is a complete transition. TENeT evolves from a 20 community prototype running on synthetic proxies into a verified production platform evaluating over 200 communities. TENeT proves that systemic health exclusion is an engineering challenge that can be mapped, measured, and solved through rigorous open source architecture.